Hello, welcome to this lecture. Before we talk about electricity, we need to talk about something you already know very well, forces. Every time you pick up your bag, kick a football, or push open a door, you are applying a contact force. These are forces where the two objects physically touch each other. But here is something more interesting. Nature has forces that work without any contact at all. You do not need to touch an object to pull it or push it. Gravity pulls you toward the earth right now, and you are not touching the earth's core. When you hold two magnets close to each other, you feel them push apart or pull together with nothing in between. These are non-contact forces: gravitational, electrostatic, and magnetic. Why does this matter? Because the force that drives electricity through your circuits, the electric force, is a non-contact force. Understanding this is the first step to understanding how circuits work. Remember, contact forces need touch. Non-contact forces do not. Let us go deeper into non-contact forces because they introduce one of the most important ideas in physics, the concept of a field. How does gravity reach out and pull the moon toward the earth across hundreds of thousands of kilometers of empty space? The answer is the gravitational field. A field is a region of space in which an object experiences a force. You cannot see a field, you cannot touch it, but its effects are very real. Every mass sets up a gravitational field around it. Every electric charge sets up an electric field around it. Every magnet sets up a magnetic field around it. There are three types of non-contact forces you need to know. One, gravitational force, acting between any two objects that have mass, always attractive. Two, electric force, acting between charged objects, can be attractive or repulsive depending on the signs of the charges. Three, magnetic force, acting on magnetic materials and on moving electric charges. The key insight is this: the field allows a force to be transmitted through empty space. This is how electricity and magnetism work at the most fundamental level. Let us now look at an idea that will help us understand voltage in a very natural way: gravitational potential energy. Imagine you are climbing to the top of a hill. The higher you go, the more potential energy your body stores. If you were to fall, all of that stored energy would convert to motion. In physics, we call this gravitational potential energy, or GPE. It is the energy an object possesses because of its height above the ground. The formula is straightforward. The change in GPE equals m times g times delta H. Here, m is the mass in kilograms, g is the gravitational field strength, approximately 9.81 newtons per kilogram, and delta H is the change in height in meters. So, a heavier object placed at a greater height stores more gravitational potential energy. Now hold this thought. Later in this lecture, when we define electric potential difference or voltage, you will see that it follows exactly the same logic, just with electric charges instead of masses and an electric field instead of gravity. Nature loves repeating its patterns. Now we come to the electric field, and we will give it a precise measurable definition. First, let us be clear about two terms that students sometimes confuse. Electrostatic force is the direct force between two charges, whereas the electric field is the region of influence that one charge creates around itself. Here is the analogy. Just as a heavy mass sets up a gravitational field around it, a charged object sets up an electric field around it. To measure electric strength at a point, we place experimentally a very small positive test charge, let us call it Q, at that point. The electric field exerts a force F on this charge. Electric field strength E is defined as the electric force per unit positive charge. E equals F divided by Q. The unit is newtons per coulomb, or equivalently volts per meter. The direction of the electric field at any point is the direction in which a positive test charge would move if placed there. This concept is foundational. Every time current flows in a circuit, it's because an electric field is pushing charges through the conductor. The battery creates the field. The field does the work. Now we come to one of the most important quantities in all of electrical engineering, the potential difference or voltage. Remember the gravitational potential energy example we discussed earlier. When we carry a mass to a greater height, you store energy in it. The stored energy is ready to do work. Electric potential difference works the same way. The potential difference V between 2 points A and B is the work done per unit charge in moving a positive charge from A to B. The formula is V equals W divided by Q. Here, W is the work done in joules and Q is the charge in coulombs. The unit of potential difference is the volt V. 1 volt equals 1 joule per coulomb. The volt is named after the Italian scientist Alessandro Volta, who invented the first electric battery in the year 1800. In your circuits, the battery creates this potential difference. It is the source of all the energy in the circuit. Voltage is the driving force. Without it, no current flows. We understand voltage now, the driving force. So what does it actually drive? It drives electric current. Electric current is the rate of flow of electric charge through a conductor. Think of water flowing through a pipe. The voltage is the pressure that pushes the water, and the current is the actual flow of water through the pipe. If a charge Q flows through a cross-section of a conductor in time t, then the current I is given by I equals Q divided by T. The SI unit of electric current is the ampere, symbol A. 1 ampere means 1 coulomb of charge passing a given point every second. The ampere is named after the French physicist and mathematician André-Marie Ampere. He laid the mathematical foundations of electromagnetism. For perspective, a small LED draws about 10 to 20 milliamps of current. A ceiling fan draws about 0.4 ampere. And a typical lightning bolt carries around 30,000 amperes for just a fraction of a second. Current is what does the actual work. It lights the lamp, heats the wire, and drives the motor. Without current, voltage is just potential waiting to be used. And now we come to a question that confuses almost every engineering student at the start. Which direction does current actually flow? In a circuit, conventional current I is shown flowing from the positive terminal through the external circuit to the negative terminal. But in a metal conductor, the particles that actually move are electrons, negatively charged, and they flow from negative terminal toward the positive terminal. That is the opposite direction. Why the confusion? The answer is historical. In the 1750s, Benjamin Franklin proposed that electricity flowed from positive to negative. This became the standard convention. Nearly a century later, scientists discovered it was actually electrons flowing the other way. But by then, all of circuit theory, the mathematical conventions, and all published books were written in terms of Franklin's convention. Rather than rewrite everything, engineers kept the original direction and named it conventional current. So remember clearly, electron flow goes from negative to positive. Conventional current goes from positive to negative. They are always in opposite directions. Both are valid. Both are used. The key is to be consistent within your analysis. As engineers, you will use conventional current throughout your entire degree program.